Good afternoon, everyone. Sorry, I can't be with you today, but Mark asked me to record a little bit about myself to introduce who we are and the work we're doing at Cambridge University. So I'm Jonathan Cullen from Cambridge University, and I am just going to share my screen. Now you've seen my face. So let's get started. So I head up the Resource Efficiency Collective at Cambridge. So that's about 10 to 15 people who are working on this idea of using energy and material resources in a better way to deliver the services that people want. So how can we do that much more efficiently? And as you know, we're part of TransFIRe, and I'm heading up the work package 1 or Workstream 1. Look forward to meeting you all, hopefully in person as well. And in that work package, we're looking at this Gentani principle of understanding the real minimum resources that you need to carry out a process, which is very similar to the resource efficiency work that I do in our group, where we're taking the idea, we're taking energy, material resources into processes or into countries, if you like, but let's keep it at processes for now, and seeing what the useful output is, maybe what the work that you can get out of that process is, or the product you're getting out, and the useful byproducts and waste. And we use something called exergy to be able to bring energy and material inputs together, and to be able to value both energy and material outputs, as well as understanding the losses much better. As part of this work package, transferring best practice by applying Gentani, there's 4 substreams, mapping the material streams, and I'll put the initials of the people involved. This is from the proposal. Looking at process and equipment models and really trying to work out whether there's kind of cross-sector types of activities, drying, granulation, heating, which we might be able to optimize or at least benchmark for industries. Benchmarking performance of the sectors, so steel plants, chemical plants, glass plants within those sectors, benchmarking how well they're doing, and looking at what metrics might be able to measure the performance of the UK's industrial plants, and then delivering best practice, which is working with the industry to transfer the knowledge from between academia and industry. Just to give you a bit of a view of our work, we're known for doing these kind of macro level holistic system pictures of energies and materials. This is the first one I did in my PhD, now nearly 12 years ago, which looked at global energy demand. So tracing energy demand right from the fossil fuels all the way through the different machinery, electricity, different pieces of equipment, different systems, industry there in purple, which we are focusing on, and then understanding what services this delivers to people. We've also since then mapped global steel flows, and this system view of global steel gives you this picture that all of these gray recycling flows down the bottom here. It turns out 25% of steel never makes it actually into a final product. And you can only really see that when you zoom out and see the whole picture. Similarly, aluminium flows, where now 50% of the material never makes it into a product, is cut off in manufacturing processes. And also, we've got a big problem of downcycling, where we're taking wrought scrap aluminium and putting it into cast aluminium blocks. And the problem with that is you can't once you've got cast alloys, once you've got silicon in there, you can't undo that process. And also we're running out of, as we go forward and we convert across to electric vehicles, we're going to run out of cast aluminium blocks, engine blocks, to put this aluminium into. We've recently done, just this year, a global analysis of glass, It's much simpler because there's much less data out there for glass, but that was very interesting, including a stock model of how much glass was in buildings and automotive products, which last much longer. So that was interesting. And a few years back, we did a global chemical flow map, which was the most complicated diagram we've done, about 90 different processes, each mole about balanced with realistic yields from industry, lots and lots of different intermediate products going on. And as you know, chemicals is there's not one thing, it's thousands of different materials, hundreds of thousands of different products, so a lot more complicated. Turning a little bit to the UK picture, just to give you an idea of going from global down to UK, we recently released this report called the P word, Plastics in the UK, Practical and Pervasive but Problematic, as part of a project called Surplus. It's available online there. And in that work, we did the plastic flows of the UK. And what's interesting here is these big trade flows, these imports coming in and exports going out. And that's imports of raw plastic, intermediate products, and final products. So it includes the plastic that is imported in cars that come into the country, etc. And traced those different plastic types, these colors, through to their final uses. We also pushed that, that model through into the stocks. What's interesting is there's a lot more plastic in construction, in stocks, even though there's a lot more plastic in packaging in flows. So there's this difference between stocks and flows that we found, and looked at the end of life options where only 10% of plastic waste is actually being recycled in the UK. We're still incinerating and landfilling and exporting a lot of our plastic waste. As part of the UK Fires project, where I'm a co-I, that's based in Cambridge, Julian Allwood leads that. We are currently mapping all the materials in the UK. So that's this trade flows, imports, exports, and the production flows, with detailed maps of how the materials flow through the production and manufacturing sector to use. So this is an overview. It's early work, so the diagrams aren't as pretty, but this is an overview of all the materials being used, and buildings obviously are using a lot of materials. But we can drill down further. So this is a map of just the metals flowing, not showing which ones they are, but there's aluminium, copper, steel in there, but just the processes going on. And if we zoom in again, we get down to now steel and aluminium, and this is just the metal rolling processes. So the idea is you'll be able to zoom into these Sankey diagrams, seeing more and more detail of the mass flows of these materials. And finally, just to go even down further, just to look, we did some work with Tata Steel in Port Albert, and this was looking at just the basic oxygen steel making. And now we're looking at 900 batches, real-time data, so moving data, and looking at the efficiency of this process. And it turns out that the converter on the right-hand side is the one that's got lots of variance in the efficiency because of the operation. And when we dived into that more, there's this bimodal distribution of these 900 batches because of the way the boss gases weren't being recovered at the lower efficiencies. And also we found an issue with the lid gap on the boss, which was changing the calorific value of the gas that was going to the power plant. And that was making a big difference in the second on the right-hand spike here. And when we looked overall, we had two different modes of operation, one with the boss gas, one without. So the without is the 8% loss, with is this down to about 3% loss, that's in energy. But we found equivalent amounts of exergy or value being lost as material from these processes as well, around 3% of the total input. And very few studies look at the material, so that was very important. Thank you. I'm not there to answer any questions, but I hope that gives you just a brief overview of the work we've been doing, and perhaps the kind of the holistic approach that we might take in this project, where we're trying to collect up the data to provide really good evidence for decision making about how companies and industry sectors in the UK can decarbonize, and can be operating at their most resource efficient. Thank you.